Hello, everybody. Welcome to our class, the second day of the semester. And today we will start beginning to talking about kinematics. From the word kinematics, you can probably already imagine it is a study of motion. And since we're talking about mechanics, we are looking at physics laws that describes motion, right? So we start with some kinematics quantities, and we will look at how do we use these quantities to study different kinds of motion. And this is the very beginning, the first topic of this semester. So I have been looking at the comments you have left. Some of you already did the pre-lectures for today, even though it's not counted toward the grades. I appreciate that you did it and left your comments. It is a very common thread of read that a lot of you mentioned online, that reading and interpreting graphs is difficult, and that's very much understandable. Graphical representation is a different kind of representation. So we will begin with the definition of these quantities, and we are looking at the relationship of these quantities using equations, and then we will look at a different kind of representation of using graphs. So it's very common that you find it confusing. And don't worry about it, we will go through that in class. Also, some of you have mentioned that it is very fast. The pre-lecture slide seems to be very fast. And I also want to say that is fine. And these lectures, they're not designed to replace the actual lecture. They're really designed just to give you a basic idea and kind of navigate your attention to place you find most difficulty. So for example, if you read through these lectures, you find, I think working out the formula is difficult and you pay more attention about that in class, or if you find graphs to be more difficult, so you know what to pay attention to more. So it is totally common to find these lectures to be pretty fast, and I would say I have read through these lectures and I have the same thoughts to myself. They're pretty fast, but we will go through them again in class, so don't worry about it. All right, so that being said, I will go ahead and let's turn to our lecture. I feel like I had showed my video. I wanted to say hi, but I'm not really seeing my video anyway. So I'm going to stop my video and simply just share my screen with you, okay? All right, so anytime you have a question, feel free to stop me and unmute yourself and just let me know that you have a question. Or if you type in the chat, but if I don't see you, just simply stop me. So today we will talk about the concepts. We will start with the definition of position, displacement, velocity, and acceleration. And a lot of you have mentioned in your pre-lecture notes that you find the relationship of these quantities difficult. And we will make sure we cover that. And we will talk about vectors. This is really can be a standalone subject because it is math. And the reason we are talking about vectors here is because these quantities are vectors. So I don't want to talk about the math standalone. I want to talk about the math in the context of our physics. So this is the theme later on when I talk about the scalar product, the dot product. We'll talk about the cross product of two vectors. I will not talk all about that separately. I'll talk about it when we get to use it in physics. So here, I simply wanted to mention a little bit about vectors because the quantities we are dealing with are vectors. And then we'll use these definition to help us describe motion. That's our goal of kinematics, right? So we start with the basic one-dimensional motion, the most simplest motion that we can study using these quantities. So this is what we try to do today. So physics is a abstract language, but it doesn't have to be. Sometimes we just need to build a little bridge between the abstract physics and something we're very familiar ourselves. For example, when describing motion, a lot of you probably have experience doing this already. We can simply take pictures of a motion, right? For example, imagine that you are trying to film a long jump or whatever other motion you're thinking about, you want to show the process. So you simply have a camera that take a picture every, let's say, 0.05 seconds, very fast, and you can put all these frames together. So you end up with is a object that is moving and is changing its position in space as time goes on. So you end up with something called a motion diagram. I'm sure this is not an abstract idea. This is something we're all familiar with. And this is what physics is built upon. It starts with something concrete. We're trying to make it a little bit more abstract. So this is, so first of all, in describing motion, physicists write to draw a motion diagram to describe how an object moves in space as time goes on. So imagine if I'm talking about me walking across the room, and you try to draw the motion diagram of me walking across the room, you'll end up with this little diagram right here, right? You have one person and it's changing her position in space as time goes on. Let's say I want you to draw my position every second. Okay, so these are equal time intervals. Here is 1 second in between and 1 second in between, 1 second in between. And you can see I'm walking with a very steady speed. So you can see that the change in my position is equal distance here and here, from here to here, to here, to here. This is it. This is a motion diagram. But later on, we'll make it a little bit more abstract. But imagine you're drawing it. I'm sure we all know how to draw it. So here I have a question about a walking motion diagram. If you are, if the scenario is a little bit different, I walk across the room, and then I stroll the first, but then I run the second half. What do you think the motion diagram will look like in this case? I will go ahead and let you vote on this question. We do not need to discuss with our peers. We simply, let's just vote. Okay, we have 94 out of 104 voted. Let's just a few more seconds so everybody can finish their voting. Okay, any last minute vote before I turn it off? All right, I'm going to end the poll and I'll share the results with you. Okay, so majority of you voted for A, and it is correct answer. Very good. So what would you say the difference between A and B is? It seems like that is the majority of the answer differ from the second popular answer, which is B. A has closer together in the beginning, right? And I'm further away later. And B had me further away at first, but they're closer together later. So what is that, the reason that you choose A or B? Anybody would like to tell us or share with us their thoughts?
Walking would mean like shorter distance versus when you run, you go faster. So it would be further.
Ah, Kimberly, thank you. So I am walking first, so I am slower at first, right? So when you look at my position, from the first second to the second second, I will have changed my position a little bit less than if I were running. So later on, I'm running. So in the second or whichever time interval you look at, I have actually gone a little bit further. So I should have a bigger gap when you are sort of, if you're taking a camera or if you're looking at drawing my position over time. Yes, so displacement over time is later on we will talk about that is your velocity, and then you can see that I have a smaller velocity at first, but then a bigger velocity later on. So A is correct. Very good. Now in physics, we'll simply, physicists are not artists, they're not good at drawing. So instead of doing something very artistic every time, they try to simplify things and make it more abstract. So, okay, so the physics motion diagram, and you don't have to worry about drawing nice pictures, is we're going to modify everything as little points. So based upon the concrete diagram we draw, we're going to do the following things, and you'll end up with a physics motion diagram. First of all is model your objects as points, or we could call them point particles. Now you might wonder, how can you do that? This is actually a modeling idea. So physicists use a lot of model. Modeling simply means that you represent something, you make assumptions to simplify it. So here, model the object, a person, a car, or whatever, as a point particle is a point particle model. The reason for that we can do that is this is a simplification. Is yes, you may, when the long jump, your arms and legs are moving around. So different parts of your body are moving differently. That is right. However, as far as what you're concerned about is the position of this person. Whether your arm is up or down doesn't really matter. Your position is still there. So I can treat you as just a point. That helped me simplify the process of simply by looking at you as a point particle. That is a point particle model. And the second, we want to define a coordinate system. You need an origin and you have a positive and negative direction. So in this case, let's imagine I have an object that is moving in space, and the position changes. I'm simply treating as a little points. I draw a lot of points. I'm going to say this is my origin. This is the starting point as in origin, and I'm defining a positive direction to be pointing to the right. So I did the first and second step. The third step, you can label the events in the order. So indicating in what order these events occur. So I'm going to say this is 0, 1, 2, 3, 4, 5. I'm sorry, these should be on the dot on the axis. So that's a motion diagram. It's nothing fancy. We simply just made something more abstract. That's all. But there are a lot of information we can read from the diagrams. And the 4 physics quantity we are going to name today are position. That's the first one we're going to look at. And displacement, and velocity, and acceleration. We'll go through them one by one. Position. Position, now that word is a colloquial word we use every day, right? So it simply tells us where you are, where the object is. So position is actually a vector. It points from the origin to the location of this object. So for example, let's say the person right now is here. I'm standing right here. Where is my position? You can think about how you might describe your words to people. My position is 100 yards away from the origin, and I'm walking to the direction of east. You might describe in those words, right? Those are exactly physics quantities. You're telling them a magnitude that is 100 yards away. You're telling them a direction. You're walking to the point of east of your origin, right? So position simply is a vector pointing from the origin to the point of interest. So in this case, my position right here is a vector pointing from 0 to number 3. So this would just be my position. I use R to represent position. This is R at the location 3. So this is my position. Position is a vector. not only it has a magnitude, it also has a direction. You have to tell people how far you are away from your origin. You have to tell people in what direction you are away from your origin, right? So that is a position vector. We use R to represent it and put a little arrow on top of it. This arrow represents that it is a vector. You need to tell people about the magnitude and the direction. So here, let me put in a little information about the math vectors. You may have already encountered this in your math class. If not, here we are. We're talking about vectors. Vectors are these quantities that have both magnitude and directions. The examples you have seen already are positions, displacement, velocity, acceleration. All of them are vectors. Now later on, we will do forces. Those are vectors because not only how much strength you apply matters, in what direction you're pulling also matters, right? Those are vectors. On the other hand, there are some other quantities has only magnitude. For example, if you want to tell people simply the distance, it's different than talking about position. You say, I have traveled 100 meters, or I have traveled 500 miles. Those are just distance. It doesn't matter what direction it is. Or you're telling people about your speed, how fast you're traveling. That is different from, so distance is different from displacement. Speed is different from velocity, because velocity has a magnitude, which is speed. That velocity also has a direction. And temperature, for example, is just a number. There is no direction. It doesn't make sense to talk about the direction of a temperature, right? So these are called scalars. These has only magnitude, but no direction. Can you, any of you give more examples about scalars? Can you give another example of what quantities do you think is a scalar?
Mass?
Mass, yeah. Just 2 kilograms. It doesn't matter in what direction it is. It doesn't even make sense to talk about directions. Very good. Any other examples?
Density?
Oh, never mind.
Density, right? Yes, density. Very good. Anything else?
Time.
Time, yes, I hear time, yes. Also scalars, excellent examples, very good. Or just so we know, volume also is a scalar. Time is scalar, temperature, all of these. You only need to tell people about the magnitude of that. So there are different ways in math we represent vectors. For example, if we have a vector and then we're looking at this vector in the x and y direction, we can represent it two ways. One way is to tell people how much it is in x and how much it is in y. Now, for example, if this arrow vector A is 3, has 3 here in x, for example, and 4 here in y, then you might say A is a vector and has 3 as an x component and 4 in the y component. Okay, now you can think about this in a more concrete way. Let's say you're traveling, okay, and this is east and this is north, and you start off here and you end up here. You have changed your position. So how do you describe to people where you are? You will say, I have traveled 3 miles east and I traveled 4 miles off to the north. So you can kind of tell people that way, right? That tells you where you are in terms of your position. And you can see this expression, maybe you have seen this already, is breaking it down into components. So this vector has 3 as the x component, 4 in the y. The x hat and y hat are simply unit vectors telling us simply the direction. It does not have any magnitude. So 3 in the x direction, 4 in the y direction. So that is one way to represent our vectors. Are there any other questions about this particular expression before I move on to talk about another way to represent vectors?
What are the little arrows on top of the X and the Y?
You mean this, right?
Yeah.
Okay, this is called a unit vector. X hat, this is called hat, which is a unit vector indicating only directions. So this simply means the X in the X direction, pointing to the right. Y hat is the Y direction. Did I answer your question? Yes, yes,
Yeah.
it is positive. If you want to do a negative direction, you will have to say negative X hat, then that points to the left. Yes. Okay. All right, so the next way that you imagine you tell people is you probably won't say I'm 3 off to the east and 4 off to the north. You will say I have traveled a total distance of 5 miles. Because your length of this, you can see, is 5. If this is 3 and 4, then it is 5. So you say I have traveled 5 away from my origin, and I'm at 45 degrees. So let's say, imagine you have traveled in a 45 degrees angle. You say, I traveled 45 degrees north of east. So you traveled in this direction, you just simply keep going until you have gone 5 miles. So most likely that's how you're going to describe where you are, right? So you can also talk about this vector as the magnitude of this vector and the direction of this vector. As the magnitude is how long this vector is. So from this tip to your origin, where 0 is, it's 5, is a magnitude of 5. So that is first thing you tell us, it has a magnitude of 5 and it has a direction of 45 degrees north of east. Or you can say 45 degrees between y of x, y above x. So that's a way that you can tell people where you are. That's another way we talk about vectors. Now, if you are given that A has a magnitude of 5 and you want to know what is AX, which means what is the X component of this vector, then you simply use A times the cosine of this angle and you get the X component. If you want to know AY, you simply use A, the magnitude times sine of this angle, you get the length of Y. So you get the length of AX this way, you get the length of AY that way. So whether they give you AX or AY, or they give you A or theta, they're giving you the same information about this vector. Okay. So now let's look at vector addition. We have multiple vectors, and a lot of times we actually add them up or subtract them. So how do we do when we have two vectors adding up? Vector addition is different from scalar addition. It's not like you do 2 plus 3 equals 5. It's not necessarily 5 now because 2 and 3 has directions. So how do we do them? There are two different methods and not all that different, but then in terms of how you operate, it might be a little bit different. So let's say you have vector 1, the red arrow pointing this way, you have vector 2, you want to add them up. The first method is called a head to tail, which means you're bringing the tail of one vector to the head of another one, and you complete it by drawing a third vector from the beginning of 1 to the end of 2. So that is 3. So 3, as in vector, is vector 1 plus vector 2. Maybe I can describe this using the idea of forces. So let's say you have someone pulling with a 1, this force pulling in this way, and someone pulling with 2. So the result of those two people pulling is equivalent to a force 3 pulling in the horizontal direction. That means the 3 is equivalent to 1 and 2 added together. That is a vector addition. And you can see the magnitude of 3 is simply not 1 plus 2. It is only 1 plus 2 in terms of how the magnitude add together if they're in the same direction, right? Because you have, let's say you have 5 in this direction and you get a 10 in this direction, they're adding together, you get 15. But if they're not in the same direction, if you add a 5 this way and you have a 10 this way, you add 5 and 10 together, you're not going to get 15. In this case, you actually get a 5 to the left if you add them up. So you can see the direction now matters in terms of adding up vectors. The second way to draw the addition is follow a parallelogram. So let's say you have a 1 and 2. I am bringing 2 so that the tip of 2 and 1 are overlapping. So I have 1 here, 2 here, and I am drawing a parallel line for 2. So I have 1 here and 2 here. To draw a parallelogram, simply draw a dashed line, which is parallel. So this is parallel to 2. And from this tip, I do a parallel line that is parallel to 1. So I got this cross point. I'm going to connect them, and that becomes 3. This is becoming my addition, my vector. You can see it's basically the same result I get before. It's just how you manipulate it is slightly different. Okay, so before I move on and actually give you some questions for we to look at, are there any questions about vectors and vector addition before we move on?
What is the equation for the parallelogram one?
There isn't an equation, it's just simply just follow a parallelogram in the sense that you got 2 lines, right? You want to draw, you just want to draw, complete this by making this parallel to this, and this is parallel to that. And you will get your vectors. In terms of, okay, if you want an equation, it still comes back to the head to tail method. As in you treat this triangle. Look at this triangle. This is one of them. Let's say that has a magnitude of A, and this has a magnitude of B, right? This is one of my vector. This is another vector. And this is the third vector, C. So you want to know the magnitude of C, you can look at this in this triangle, and I need to know the angle in between them. So I will be able to find it out. But in terms of just drawing it, you need a ruler and just to draw it. You don't really need a math formula. Does that make sense?
Yeah, it does. Thank you.
Okay. Any other questions before we move on?
For the head to tail method, how do you know what degree to set them up at?
I'm sorry, can you repeat that? The head to tail method is a question. How do you do that?
Yeah. No, you know the part where 1 and 2 connect in the head to tail method? How do you know what degree to connect them at?
Oh, so you're giving a vector 1 and you give a vector 2.
Yeah.
Right, you are moving vector. Okay, so vector 2, let's say, is drawing randomly here in space. You simply are going to move them together. But of course, when you move 2, you have to move them parallelly. So they still remain the same vector. You cannot change its position. So you have to move 2. Let's say, okay, I move it down. That's still 2. I'm going to move it down. That's still 2. I'm going to move it to the left a little bit. You bring it closer to 1 until it comes here. But it's still 2. You see, it is still pointing in the same direction, and I still have the same length. I haven't changed 2. I simply bring it over so the tail of 2 meets the head of 1. Does that make sense?
Yeah, I get it now.
Okay, and then once they meet, from here to here, you complete it with the third vector. This is simply 1 plus 2. It will become more clear as we work off these examples. So let's take a look at this question. So here we have three vectors, A and B and C. Which one of these will describe the relationship of A, B, and C? Okay. Well, I will give you guys breakout rooms, discuss it probably a minute and a half, a minute or two, and then we will come back to vote, okay? Okay, all right. If you probably need to take a screenshot of the question, so when you go to breakout room, you still know what it looks like, okay? Okay, as you come back, please put in your answer to the question in the poll. Okay, so we pretty much have all the voting, just a few more seconds so people can finish their votes. Okay, any last minute vote before I close it? Okay, I'm going to go ahead and end the poll, and then let's take a look at the results. We have a majority of you voted for B, and then the rest of the time pretty much tied, A and D and E. Let's take a look at this together. So there are different relationships talking about A and B and C together. So So whichever one that you guys chose, what method do you use? How do you find out the relationship between them?
Head to tail method.
Head to tail. So in this case, you connect two vectors head to tail. Which two vectors do you connect to get another one?
A and C.
And
A and C. You can see A and C are connect exactly head to tail. So because of head to tail method, we know A plus C is equal to which one? B. B, yes. So that is exactly the relationship you're looking for. You can see you simply have to move B to the other side and you get A minus B plus C equals 0. And indeed, B is correct answer, very good. So minus B is simply going to be a B flipped directions. You have a vector and you flip it to the opposite direction. And we will actually look at a question that's like that later on. So here you have already know how to do addition. Now I'm giving you another one that's doing subtraction. So A minus B. I give you a hint already that minus of something is a vector that is flipped in a different direction. So this is equivalent to asking what is A plus negative B? You still are doing vector additions by simply you're adding a vector that is in the flip direction. So that is just a way for us to do subtraction, okay? All right, so this one, I will let you guys vote here, just not to go to breakout rooms. You can take about a minute or so, minute or two to do the poll, okay? I'll wait here. And if you want to discuss with one another, you feel free to, or if you want to use the chat room, you can do that too. Okay, let's take a few more seconds to finish our voting. Okay, any last minute vote before I end poll? Okay, I'm going to go ahead and close it and then let's take a look. We're pretty much tied for choice A and B. And let's take a look this together. So it seems to be we feel like the answer would be either 1 or 2 for A minus B. There are actually more than one way to get the answer. I would like to hear anybody who share their thoughts with us. How do you go about finding A minus B?
Can I go?
Yes, Sergio?
Oh, okay. So I chose B because I looked at the thing you said where A plus negative B, and I thought negative B would be a vector of the distance just facing the opposite direction.
Okay, so you have chose to do A plus negative B, right?
Yeah.
Okay, so let's see
And
how
I thought
that, okay, so here, do we have any vector that represent minus B?
3
3, yeah, 3
and it has the
seems
same
minus
direction.
B. Yeah, so we already have a vector here we can work with. So now we just need to add A and 3 together. And here, since 3 and A are already positioned in such a way that their tail overlap, maybe a parallelogram would be a little bit more easier, where you form a dashed line here parallel to 3, and you form another line that's parallel to A, and you connect this point and this point, and now you get A plus 3 equals 2. And 3 is negative B. So A plus negative B is 2. So 2 becomes A minus B. Very good. That is one way to do this. There is another way to do this. Let's say I'm not comfortable working with minus signs. I want just to work with additions. So I want to say, okay, A minus B is represented by which vector? I don't know. But I want to say if A minus B is this vector that's telling me A plus which vector gives me B, right? So A plus which vector gives me B? And you can look at all these vectors and you realize actually A plus 2 gives me B. Again, you can do head to tail or you can do parallelogram in this case. Oh, I'm sorry.
Sorry, I have a question.
Yes, go ahead.
So can you tell me, based on what you said, like A plus B gives us B, A plus 2 gives us B?
So you are asking, are you asking here, right?
I'm asking like how you got 2, like, you know.
Oh, how do I get 2? So to do A minus B is equivalent to do A plus 3. Do you agree?
Yes.
Okay, because 3 is minus B, right? So do A plus minus B is equivalent to do A plus 3. This is exactly 3. So A and 3. Okay, so maybe head to tail, you'll be more comfortable with head to tail. Let me just do this again using head to tail method. I have an A here. I need to add a 3, and 3 is here. Okay, so I need to move one of the vectors to be so that the tail of this vector overlap with the head of another vector. So how am I going to move A so that they can overlap? I need to move A up, right? You simply think of this if this is a stick. You're moving it up. I'm moving it up, okay? So I moved A up. You can see here, this is the same length as A and the same direction. I moved it parallelly. I moved A up. This is A. And now the tail of A overlaps with the tip, the head of 3. I can complete A plus 3 by drawing another vector 2 and 2 is exactly 3 plus a, right?
Okay.
That's the head to tail method. In this case, the head of 3 are overlapping with the tail of 2, tail of a, and gives me an overall vector that is 2, which is a plus 3. So because a plus 3 gives me 2, I know a minus b gives me 2. Did I answer your question?
Yeah, just a quick question. So at the beginning of the head to tail, you said A and 3 are the same.
I said minus b and
B
3
and
are
B.
the same.
Oh, okay.
Yeah, minus b and 3 are the same.
Okay, thank you. Yeah,
Because
then
you can see 3 is simply b flipped to the other side, 180 degrees, right?
yeah.
Okay, very good. All right, so that is answer is A. So that is position. So now let's change gears. We're now shifting away from math. We have learned a little bit about vectors. Now we're going back to use it in discussion of our kinematics quantities. We had talked about position. Position is a vector pointing from the origin to the point of interest. Now we're also talking about something called displacement. Displacement, the word is very intuitive. You have displaced yourself, right? You have changed where you are. So displacement is simply the change in position. I don't know when we'll get on campus again, but here we have a little campus map right here. Imagine if you are treating this point as your origin right here, and you have identified a few points here in Temple and Kellogg Drive as in your position over the time. So at point 0, you have a position. Now, the position at 0 is simply going to be the vector pointing from the origin to 0. So that is your position there. Now you keep driving and you pass point 1 and then you end up with point 2. Right? The position of 2 is what? Is from the origin to 2, and then you going to draw a vector. This is your position at point 2. If you want to talk about what is my displacement from 0 to 2, what is my change in position from 0 to 2? And that is another vector pointing from your beginning of your initial position to your final position. So it's a vector here, right here, that is delta r. Now delta r is exactly the change where you are now, which is R2, and where you were, which is R0. So it's R2 minus R0. The change in position give you displacement. And you can see from, in terms of the vectors, they indeed is correct. Delta R is indeed R2 minus R0. You can work out that head to tail method in your own time, or if you wanted to look at it real quick here, R0 plus delta R give you R2, right? So because R0 and delta R are connected head to tail. So displacement, you only need to memorize 2 events. Displacement has to do with your beginning position, your final position, and you draw a vector pointing from your beginning to the end. That is exactly a displacement. The displacement is also a vector because not only how far you have gone from 0 to 2, in which direction you have gone also matters. It is different from the word distance because distance is actually the actual route. So you can never really jump from 0 to 2 directly, right? Imagine if you were driving, you go in terms of blue line. So you actually covered the distance, which is much longer than in this case, the displacement from 0 to 2. So distance is the actual route you cover. Displacement only cares about the beginning and the end. So if this is your beginning and this is your end, let's say you kind of zigzag, zigzag, zigzag to your beginning to the end. So you covered, this is your distance. But in terms of displacement, it doesn't really care what's your actual route. It only cares from the beginning to the end, the straight line going from beginning to the end. That is your magnitude of your displacement. Okay, so be careful the distance and displacement are actually different. So let's look at this question. I think that will help us understand this much better. We have an ant crawling in a half a circle, and I'm asking from here to here, what is the distance the ant traveled and what is the displacement the ant traveled? Here I'm only asking about the magnitude of the displacement, not the direction. So I'll go ahead and launch the poll, and please go ahead and put in your vote for this one. Let's take about 30 seconds to finish this voting. Okay, any last minute vote before I close it? Okay, I'm going to end poll and let's take a look. We have a majority of agreement for C. Let's take a look. Okay, so let's look at the distance traveled. Very good. It's from here to here. You actually follow this curve, right? And that's half of your circumference, which is pi r. Very good. And displacement. Now displacement is a direct line from beginning to the end going up. So that's 2r. Yeah, so C is correct. Very good. We can see that displacement, the distance are different. Not only that one of them is a vector, the other is a scalar, the magnitude of it can be different as well. So now let's talk about velocity. We have talked about the position, displacement, and now the next thing is velocity. The velocity is simply your displacement over time. So we have two kinds of velocities. The average velocity is simply looking at how fast you're going over a certain amount of time, on average, how fast you're going. So you have changed your position, okay? You have changed your position. We use delta to represent the change, which is displacement. Delta R is your displacement over some amount of time. You use displacement over time, which is your average velocity. You can see it's a little bit different from when we say speed, right? Speed, sometimes we use distance over time to get our speed. Velocity is your displacement over time. So if I'm looking at my displacement from point 0 to 1, so it's an arrow pointing this way. From this point to the next point is another arrow, so I have different displacement over time, right? And I have different average velocities over time. So this is it. This is basically we talk about as velocities. Some of you have asked about the difference between instantaneous velocity versus average velocity. It's really just average velocity describing something on average. It's not very accurate, right? It doesn't really give you what is going on at an instant, at a moment, how fast you're going, in what direction you're going. Imagine if you're going in the zigzag curved path. If I'm looking at a displacement from here to here, I'm looking at a delta t from here to here. I'm only getting sort of an idea how fast you're going from one point to another, but in every point along the way, you might have a different velocity in every point along the way. So in order to get a velocity at one particular moment, we use this idea in math is you're taking the limit, right? You're taking a limit so that when you look at 2 points, these 2 points are so close together, it's basically 1 point. Then you're narrowing it down to your velocity at that instant. So here I'm taking the limit of delta t goes to 0, which is I'm basically looking at 2 points that's so close to each other. And then the delta r over delta t gives me the velocity at that instant. And in calculus, this is equivalent of taking a derivative. So an instantaneous velocity is the derivative of your position over time. So that is a very important relationship, okay? Is dr over dt give you velocities. Okay, that's the difference between instantaneous velocity and average velocity. That's something you have asked about in your pre-lectures. Any questions before I move on this particular topic? Okay, so velocity is a vector. The magnitude is AKA speed, how fast you're going. You are telling people, I'm driving 50 miles per hour. Now I'm telling them my speed. If you're saying I'm driving east with 50 miles per hour, you're also telling them in what direction you're going. So you have told them your velocity, both the magnitude and the direction in which way you're traveling. So the next question is actually interpreting some different graphs is from the object path. Can we tell the direction of the velocity? So I'm going to go to this graph again. You can see that when these 2 points are so close to each other, and I'm looking at the direction of delta r, because the direction of velocities, you can see the direction of velocities is basically given by the direction of displacement, because time is a scalar. So if you want to know the direction of the velocity, you need to know in what direction you have changed your position, the displacement. So when these 2 points are so close to another, this little arrow represented here is your displacement delta r, dr, when t is really small. And that is your velocity. And you can see represented on the graph is as if I'm simply drawing a tangential line right here at this point, and that gives me the direction of my velocities. So if you have a curve, which is the path you're taking, you want to know your velocities, you simply draw a tangential line at any given points, and that gives you the velocity. Okay, so here, that gives you the velocities. So, for example, I give you this question. The blue line shows you the path of an object and position 1 and 2. So which of these vectors best representing the velocities at P1 and P2? So I have just already told you how you can get velocities from the curve. I'm going to let you go ahead and vote on that. Okay, let's take about another 20 seconds to finish our voting. Okay, any last minute vote? Okay, I'm going to go ahead and end this and then let's take a look at our results together. You can see that we have majority choose for B and some choose for A as well. Let's take a look. So to look at point 1 and 2, right? You can see that we have just learned this cool technique. If we just need to find a tangential line, you can see that maybe we won't be able to draw it exactly. We just need to know the overall kind of trend which these vectors are going. So you can see the tangential line here is like in this direction. And this one is actually a little bit downward, right? So to look at these seems to be, this is the best representation of the direction of your velocities. So which is up a little, one is up a little, one is down a little, okay? So 2 is, B2 is the correct answer. So we have talked about velocities, and the next thing is the acceleration. You can use the analogy of velocities in relationship to position to get the acceleration. So now it's not like you're learning things all from scratch again. So here, velocity is a rate of change in position. So we have talked about velocity V is, we talk about average velocity V is delta R over delta T, the change in position over time. Instantaneous velocity, you're simply just taking derivative by making the 2 points are so close together, so dr over dt. Now this is the rate of change. Rate, how fast you're changing it, right? So you're changing your dr over so much time, so how fast you're changing. So using the analogy, we can write acceleration is a rate of change in velocity. So it's, instead of dr, is dv over dt. And likewise, average velocity, instantaneous velocity at any instant is dv over dt. So I'm doing this in pure analogy to velocity with respect to position and its acceleration with respect to velocity. So here you can think of how fast is my velocity is changing. And this is talking about how fast is my position changing. One gives you velocity, the other gives you acceleration. Okay. Now, you can see if I replace my v here, v is dr over dt, I get that my acceleration is the second derivative of position with respect to time, okay? So again, that is a very important relationship as well. So if I would say, if there's one thing you need, 2 things you need to make sure you do is you need to remember this and you need to know this, okay? Acceleration is also a vector, and you can see the units is meter over second square because you can see it's change in velocity. Velocity give you the units of meter of second and time give you seconds. So you get meters over second square as in the units for acceleration. Now the direction is in which direction your velocity is changing. And that can be a little bit tricky. So for example, so if your first velocity is this way, v1, and the second velocity is this way, v2, you can see your velocity is in the same direction but had increased, right? So the change of velocity seems to be pointing to the right, and that is delta v, which gives you the direction for your acceleration. You are accelerating to the right, you're speeding up in this case. So let's look at this question because it gives us an idea of how to get acceleration from the change in velocities. Okay, I'm going to walk you through this question instead of voting because there's a little bit something I want to cover as well. So in this diagram, it's showing you a velocity in two different moments, v1 and v2. Okay, so imagine, let's say you're driving to this way first, and then the next instant you're actually driving this way. So to actually have this change in velocity, what kind of acceleration do you need? Now you need to find the change in position because your acceleration will be the same direction as your change in your velocity. So delta V is V2 minus V1 is the change in position, in accelerate, in velocities. So you can see the delta V, this is V1, this is V2. I want to do V2 minus V1. I have two choices. I can do V2 plus negative V1. So I can do V2 plus negative V1, and that seems to give me a direction going down this way. That's delta V. Or I can do V1 seems to be V1 plus delta V gives me V2, and I can also find my delta V this way. So my delta V is pointing diagonally downward, which means my acceleration is in this way. So just think about it. If you were driving up sort of like this, right? And then think about in which way you have to be pulled yourself down in order for you to drive downward like this. You need an acceleration going downward, right? So it makes sense for your acceleration, or if you feel a force, to be pointing in this direction, as in delta V. Okay, so this is really just something to show you again, how are we using vectors to give us the relationship between velocities and accelerations. So here's a summary, and that's something you could read later. It's basically summarize the concepts of all the quantities that we talked about. There is something subtle about acceleration and velocity. So let's look at this particular question. We have a car, and showing that our motion diagram of dot starting and going to the left, and our speed keeps going up and up, right? Driving to the left. So here, what would you consider to be the sign of an acceleration? Here, whether something is positive or negative, depending on which way do you define to be positive. I have defined something pointing to the right to be a positive direction. And here I'm asking you, what is the sign of the acceleration in this case? Okay, I'll go ahead and let you vote on this one.
Professor, is option B the hyphen? Is it supposed to be like the arrows that are moved, like the long strip of like line?
Is there a question, Ryan?
Yeah, for option B, it says is that a minus sign or a hyphen? Like, is it supposed to represent like the line?
Oh, yeah, sorry. That's just negative. B simply means.
Oh, okay.
Yeah.
Okay, thank you.
Yeah, sorry about that. Let's take about another 20 seconds to finish the vote, okay? Okay, let's take a look. So we're pretty much tied between positive and negative, slightly more people voting for negative. So how are we going to decide the sign of an acceleration? What do you think? Instead of asking you the sign, if I had asked you a different question, I say, in what direction is the acceleration pointing at? What would you tell me?
Negative.
Your acceleration is pointing to
The left.
Left.
left. Yes. So you can see that you're speeding up to the left and get higher, higher, faster and faster. So you must have an acceleration pointing in the same direction. Very good. So acceleration pointing to the left has nothing to do with something being positive or negative. It only will have a sign once you have defined what a positive direction is. In this case, we want right to be positive. You could very well define your left to be positive. That's totally up to you, okay? So in this case, because acceleration is pointing to the left, and I have defined the right direction to be a positive direction, and therefore my acceleration is negative. A negative acceleration doesn't mean anything about something being speeding up or slowing down, okay? You're looking at, okay, is your acceleration in the same direction as your velocity? They might be both positive, then they're speeding up, or they might be both negative. In this case, they're speeding up. One positive, one negative, which means they're in two different directions, and then they're slowing down. Does that make sense? So in this case, yes, the answer is B. So the one point takeaway message I want you to remember is whether velocity or acceleration being positive or negative depends on your choice of your coordinates. You can decide whichever positive to be a positive direction. Yes, someone said slowing down means increasing in speed in the opposite direction. So I would say it's increasing velocity in the opposite direction because speed is a scalar. Yes, so slowing down, something is slowing down, okay? Which means you have a change in position a change in velocity in the opposite direction, which means you have an acceleration in the opposite direction. Yeah, it's like you're increasing your velocity in the opposite direction. Another takeaway message, and then we will end the class for today, is if I tell you the velocity of an object at certain moment is 0, can we conclude the acceleration also be 0 or non-zero? So basically saying if v is 0, does that mean a has to be 0 or non-zero in this case? I'm asking you to vote on non-zero. Is it possible that a could be non-zero? We don't have time to vote, so I just want you to maybe share a thought or two. When v is 0, can a be non-zero? Is it possible? Yes, it is possible. And can you give me an example?
And something stops.
Like you're going in this direction, but someone is giving you an acceleration in the back, in the opposite direction, and eventually you stopped, right?
Like when,
Yeah, you come to a stop momentarily, but then next second you're starting to speeding up in the opposite directions, right? Because you have an acceleration that way.
like
Yeah.
like when
I'm
a
sorry.
car stops at a stop sign.
The car stops, yes, but then at that moment your acceleration is also 0 because you come to a complete stop. You completely stopped. Does that make sense? The acceleration leading up to that moment is non-zero, but at that moment it's also 0. So an example would be, imagine you are throwing an object up in the air. So you're throwing a ball up in the air, the ball will slow down because eventually it falls back down, right? So throwing it upward, a ball goes upward and it stops. It goes to the highest point and stops. and then falling back down. It comes back down. During this process, you're feeling an acceleration, which is a gravitational acceleration that is pointing downward at all times. So that's an example that this is choice is A. So the takeaway message for you is the velocity 0 doesn't mean that acceleration is 0 and vice versa. Okay, so that's all for today. We have discussed these quantities, and next time we'll continue to look at representing these quantities using different graphs. That's one of the difficult part that you guys have mentioned. All right, thank you all, and I'll see you next week.
Thanks, Professor. Have a good day.
Bye,
Thank you,
Professor.
Professor.
Bye-bye.
Have a good day.
Professor.
Thank you.
Thank you, Professor. Have a good weekend.
Thank you.
See you next week, Professor.
Thank you, Professor.
Homework is already available online on Flipped Physics, okay? Or maybe it will be available tomorrow on Fridays.
Sorry, where are you gonna post the homework again?
It's on Flipped Physics.
Okay, and just a question: do we have to sign up with our school email or just personal email?
School, it doesn't matter which email. Some people may have difficulty with the school email. Then in that case, I recommend just using another email to try.
Okay, and after we sign up, we can automatically see your homework and stuff, right? Like we don't have to like put any class code.
Yes. Yes, you sign up and you use that code I give you in the syllabus to be enrolled in the course. And then
Okay,
you
it's
do the
in the
homework.
syllabus, right?
Yes, yes.
All right, and also, where do you post the pre-labs?
What pre-lab?
Oh, I mean, you know, like,
Lecture?
sorry, what was that?
Is it pre-lecture? That's
Yeah,
on
pre-lecture.
Flipped Physics as well.
Oh, flip of it. Okay. All right. Thank you very much.
Okay, no problem.
Oh, and also, do we, when I went to the bookstore, they gave me the book too. Do we need that or?
I don't use the Holiday and Resonate. You don't have to buy it. We have this OpenStack textbook that's free online. I have the link in the syllabus.
Okay, so I should just go return it, right?
Yes.
All right. Thank you very much. Have a nice day.